So this is arguably optional, but it simplifies some things in the proof of the correctness of RSA. So the Chinese the Chinese remainder theorem is a more general fact than this, and it has to do with uh, ring isomorphisms and some other things that we just don't have the vocabulary for. But this is sort of what it means in practice for us, and it still needs some explanation. So it basically says that if you're working modulo n, and n is the product of two numbers which are relatively prime, but we just, because of RSA, we really only care when they're actually prime, but this would all be true if they were just relatively prime. Then working mod n is sort of the same as working in pairs of numbers where the first number is reduced to mod p and the second number is reduced to mod q. So all of that is incredibly complicated. So let's try to give an example. So let's say we're working, or say we're working with n equals, what should we do, 15? Everybody uses 15. Let's not use 15. Let's use 35, okay? So 35 is equal to 5 times 7, all right? So first we have to give a correspondence between Zn, so that's Z35 is equal to the numbers 0, 1, 2, ... up to 34. And so what do we mean by Z mod 5 cross Z7? So this is pairs of numbers where the first element of the pair is mod 5 and the second element of the pair is mod 7. So first I'll describe it kind of abstractly here. So it's the set of all pairs A, B, such that A is a member of Z5 and B is a member of Z7. So what does it actually look like in practice? I'm going to pause the video while I write it out so I don't bore you. Okay, so this is the set of all pairs of numbers such that the first number is from Z5 and the second number is from Z7. So who cares? The point is that you might have some complicated thing that you want to do to a number mod 35, like for example raising it to a certain power. Like let's say we take something that like 6 is a member of the multiplicative group mod 35, and maybe we want to take this to the 17th power, which isn't too bad. We just care what it is mod 35. So the Chinese remainder theorem tells us that instead of working with 6, we can go into this sort of pair world, and then do some work here, which is simpler because the numbers are smaller. And then once we find the solution in the pair system, then we come back to the answer mod 35. Okay, so let's see how this is going to work. So we need a map between Z mod 35 and Z5 cross Z7. And it turns out that the simplest thing you can think of actually works. So if we take A in here, just any element of this, and we send it to the pair A mod 5 comma A mod 7, a lot of this map has a lot of good properties. So for one thing, it's 1-to-1. So you can see that there are obviously 35 elements here because of, you can multiply, and there are 35 elements here too. And this is a a one-to-one correspondence. So if that means that no two numbers from Z35 ever land on the same pair, and also for every pair there is some element here that lands on it, and that requires some argument, which we'll give in a second. So it's a one-to-one correspondence, but more than that, sort of like arithmetic down here is just the same as arithmetic up here, and vice versa. So let's give an example. Let's actually use this example, 6 to the 17th. So first, let's just practice sending 6 into and out of the pair. So 6 is an element of Z35, and we want to send this into Z5 cross Z7. And so what element does it go to? It goes to Z mod 5, comma, sorry, 6 mod 5, comma, 6 mod 7. And so this is 1 mod 5, and mod 7, it is still just 6, okay? And now the question sort of is, how do you get from a pair back up to where it came from? So that's sort of the hard thing about the Chinese remainder theorem. So once you take the element, you go down into the pair system, and then you want to take a pair back up to Z mod 35. How does that mapping work? So let's just do an example here for this one. So when we go from the pair back up to Z mod 35, what we want is some element which is congruent to 1 mod 5 and is congruent to 6 mod 7. So how can we sort of cook up an element like that? So there's a smart idea, which is so we want x to be congruent to 1 mod 5. So we'll put in a 1 there, but we want this 1 to sort of be irrelevant down in the 7 case. So we'll multiply it times 7 so that this part will vanish when we're evaluating mod 7. However, this multiplication by 7 will sort of affect the result mod 5. So how do you stop that from happening? You multiply it by 7 inverse mod 5. So this will be 7 inverse mod 5. Okay, so now something really cool has happened, which is this number will be 1 mod 5 and 0 mod 7. So we sort of fixed half the problem here. Alright, but now we have the issue that x is also supposed to be congruent to 6 mod 7. So we'll just add a 6 here, and the only thing is we want this 6 to sort of disappear when we're considering things mod 5. So we'll multiply in a 5, and that will make this part vanish when we evaluate mod 5. Unfortunately, multiplying by 5 is sort of messed things up down here, mod 7. But we can fix that by multiplying by 5 inverse mod 7. Okay, so look, this is really nice. You've got a number which is congruent to 1 mod 5, and you've got that same number is congruent to 6 mod 7, and so it's a solution to this system of equations. And when we figure out what it is, that number will take us sort of back up into Z35. So we already know, because we're cooking up this problem, that the answer is 6. But let's just figure things out and make sure that that actually happens. So what is Z inverse mod 5? This is the same thing as 2 inverse mod 5. And what is 2 inverse mod 5? It's 3 mod 5. Okay, and at the same time we'll just figure out 5 inverse here. So 5 inverse mod 7. Can you make 5 go into 36? No. What you really need is like some multiple of 7 that ends in a 4 or a 9. Can anybody think of one of those? I'm going to cheat and just use Sage to figure this out. I could use the extended Euclidean algorithm. Should I be just like some kind of ubermensch and do this? Yeah. Um, I'm just going to figure this out using the extended Euclidean algorithm. So 7 is equal to 1 times 5 plus 2, and 5 is equal to 2 times 2 plus 1. So that means 1 is equal to 5 minus 2 times 2, but 2 is equal to 7 minus 5. So this is 5 minus 7 minus 5 times 2. All right, and so what have I got here? I've got 5 minus, 5 minus 2 times 7. Plus 2 times 5, which gives 3 5s, so 3 times 5, and negative 2 7s. All right, and so that means that 5 inverse mod 7 is 3. Yeah, obviously, I'm an idiot. Okay, so 3 times 5 is 15, which is 1 mod 7. Okay, so let's erase all this. Make the eraser a little bigger to make it go faster. Psycho killer, qu'est-ce que c'est? All right, so now we're actually ready to compute x. X should be equal to 1 times 7 times 3 plus 6 times 5 times 3 mod 35. So what is this? This is 21 plus 90, which is mod 35. This is 21 plus 20, which is 41. That's because 35 goes evenly into 70. So you've got 41, which is the same thing as 6. Okay. And so indeed this thing does land again inside 6. So to give the now if we just do the procedure in the abstract here and give a formula, then whenever we have some number x in z mod n, then this gets sent down into the pair system, and the pair that it goes to is just x mod p comma x mod q. And let's just say that you have sort of a generic pair down here. How do you get back up to the big system, which is mod n? You have, how did we do it before? Let's sort of imitate our example. Yeah, okay. So we have a times q times q inverse mod p plus b times p inverse mod q. And this whole thing has to be reduced mod pq. Okay, so now we can go into the pair system and out of the pair system. And not only is it a one-to-one mapping, but it's a homomorphism, meaning that if I do multiplication down here and then go back, then it's like consistent. So let me actually try to spell that out a little bit more. So what do I mean when I say that it's a homomorphism? That means that if I do let's say x plus y mod 35, then down here in the pair world, maybe I have x mod 5 comma x mod 7 plus y mod 5 comma y mod 7. And so you can evaluate this plus down in, in z5 cross z7, and it will be something. So just to be concrete, let's work with some actual numbers. So maybe x is equal to 17 and y is equal to 30. Okay. So we want to do x plus y mod 35, so of course that is 47, which is 12. So we know that the answer up here should be, congruent to 12. If we come down here and we do it in the pair space, then what do we get? 17 mod 5 is 2, and 17 mod 7 is 3, and we're adding that to 30 mod 5, which is 0, and 30 mod 7, which is 2. And so the result is 2 comma 5. So the question now is, if I take 235 back up to z35, is this going to be consistent? So is if I lift this back up, am I going to get 12, which is what I should get? And the answer is yes, and I will leave that as an exercise. And so this means that if you, while you're down in the pair space, you can do arithmetic and then take the result back up, and you get a consistent result. So it's as if you'd done the same operation in z mod 35 in the first place. So show that this is equal to 12. So that's an exercise. Show that the pair 2 comma 5 lifts back up to 12. Okay. And I did this example with addition, but the same thing is true with multiplication, and that's what we mean by a homomorphism. So arithmetic mod 35 is really just the same as arithmetic mod C5 cross C37. So with that understanding, let's come back to our original motivating problem, which was to figure out 6 to the 17th power mod 35. So we want to know, what is 6 to the 17th power mod 35? Okay, so this is a big number. Maybe it will be easier if I work in the pair space. So this is the same thing as, first we'll reduce 6 into its pair. So this would be 6 mod 5, 6 mod 7 to the 17th power. Okay, and the fact that these two are the same, I'm using the homomorphism property. So 6 mod 5 is 1, 6 mod 7 is 6. By the way, this is the same thing as 1 comma minus 1. And so that will make our arithmetic much easier, because it's very easy to raise 1 to various powers. So this is obviously just, so what does this even mean? What does it mean to multiply AB times CD down here? It just means AC times BD, just like the obvious thing. So what this is just 1 times negative 1. So this is the same thing as 1 to the 17th power, comma, negative 1 to the 17th power. And in this coordinate it's mod 5, and in this coordinate it's mod 7. But it's pretty easy to see that this is still just going to be 1 comma minus 1, right? So now to finally answer the question and see what is 6 to the 17th power, all I need to do is send 1 back up to z mod 35. So now I want to lift 1 minus 1 back into z sub 35. So how can I do this? I have to solve x is congruent to 1 mod 5, and x is congruent to negative 1 mod 7. Let's just work with 6. Okay, same thing. So what is x? X is equal to 1 times 7 times 7 inverse mod 5 plus 6 times 5 times 5 inverse mod 7. And we've already figured out what these numbers are. So the inverse of 7 mod 5 is 3. And the inverse of 5 mod 7 is, what did we say that was? 3? Also 3? That makes sense, right? So this is plus 6 times 5 times 3, and this is all mod 35, so this is really a congruence. So what is it? This is 21 plus 90. Oh, interesting. So it's just 6 mod 35. So we've already actually done this, and this is the same thing as 21 plus 20, which is 41, which is 6 mod 35. So what we've discovered is that 6 to the 17th power mod 35 is 6. So let's just confirm that that's true. So we have 6 squared is 1. Oh, this kind of explains it, right? So then 6 squared squared is 1, and then 6 squared 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 is 1, and I'm just squaring each previous one. So squaring the previous one, you get 6 to the 16 is 1. So now I multiply both sides by 6, and I get 6 to the 17th is congruent to 6 mod 35. Okay, so it worked. All right, and I think we know everything we need to know about the Chinese remainder theorem, so I'm going to stop the video.